Here I will explain first order low pass Butterworth filter analysis. Here active element is an op amp. Here we use active element and some passive elements. Passive elements are resistances and capacitance. Combination of both active element and passive elements. This one is the first order low pass Butterworth filter that uses an RC network for filtering. This is the RC network for filtering. Op amp is used in the non-inverting configuration. This is the op amp is used in the non-inverting configuration. Hence, it does not load down the RC network. Resistors R1 and RF determine the gain of the filters. Resistors R1 and RF determine the gain of the filter. Therefore, AF is equal to op amp is in non-inverting configuration. Gain of that op amp in that configuration is AF is equal to 1 plus RF by 1 plus RF by R1. 1 plus RF by R1. This one is the second figure. Frequency response of that first order low pass Butterworth filter. Here, first point at low frequencies. That means this is the low frequency range. F less than FH. At low frequency range, F less than FH. Gain of that voltage gain is represented by mod A. Magnitude of that voltage gain is represented by mod A. Mod A is equal to mod V naught by V in. Output voltage by input voltage. At F less than or equal to FH, less than FH. Therefore, mod A is equal to mod V naught by V in is equal to AF. AF pass gain, that is called as a pass band gain. It allows only low frequencies, attenuate the high frequencies. At F is equal to FH, mod A is equal to mod V naught by V in is equal to 1 by root 2 times AF. 1 by root 2 times AF. Third one, get F greater than FH, mod A is equal to mod V naught by V in is less than AF, is less than AF. This is the first band. One is a stop band. In the stop band, the gain is a roll off at the rate of 20 dB per decade. The gain is decreases in the stop band rate of 20 dB per decade. Slope is minus 20 dB per decade. Minus 20 dB per decade. Next one is a transfer function analysis. Calculate the transfer function of that low pass, first order low pass Butterworth filter. By using that filter circuit here, R and A, R and C filter circuit here. Consider this filter circuit. This one is resistance. Generally, we use a potentiometer. By varying that potentiometer value, we need to set the cutoff frequency of the filter. Cutoff frequency of the filter here. This one is V in R C RC. See the here A point and the B point here. A. This A point is connected to op amp. Inverting terminal. Non-inverting terminal is this one is plus. This one is plus and this one is minus. This is the op amp. Plus and minus. Consider this op amp, this filter circuit are capacitive reactance Xc is equal to 1 by j omega c. Transform into S domain. S is equal to j omega. SC is equal to J omega, therefore SC. The capacitor is replaced with 1 by SC. This one is V in. This one is V in. This one is VA. This one is VA. Find out this voltage, VA voltage. By using potential division rule, VA is equal to voltage across this capacitance is equal. Total voltage applied to the circuit is V in into this impedance of that capacitance 1 by SC by R plus 1 by SC. R plus 1 by SC. Therefore, VA is equal to V in by SC or SC plus 1 by SC is cancelled. Therefore, VA is equal to V in by 1 plus here SC is equal to J omega. S is equal to J omega RC. J omega RC. This one is VA. VA is equal to V in divided by 1 plus J omega is equal to 2 pi F into RC. 2 pi F into RC. In this diagram, according to virtual ground concept, VID is equal to 0. Here, VID is equal to 0. VID is equal to 0 means difference between these two voltages are equal to 0. VA minus VB is equal to 0. Therefore, VA is equal to VB. VA is equal to VB. Consider this one. This is the op amp. This one is resistance. Capacitance C. V in. This one is plus. This one is minus. VA. R1. V0. RL. This one is RF. This one is RF. Here 1 plus RF by R. Okay. Here VB apply nodal analysis. Apply nodal analysis at point B. That is node voltage is VB. That node voltage VB into some admittances are connected to that node BR. This one is A, this one is B. These admittances are 1 by RF plus 1 by R1 minus V0 by RF minus 0 by R1 is equal to 0. 0. Therefore, VB into R1 plus RF by R1 RF is equal to V0 by RF. RF is cancelled. Therefore, V0 is equal to VB into 1 plus RF by R1. But 1 plus RF by R1 is the gain of the op amp is in non-inverting configuration, that is AF. We know that VA is equal to VB. VA is equal to VB. Therefore, VB is equal to VA into AF. but VA is equal to V in by 1 plus J 2 pi F RC. VA is equal to V in by 1 plus J 2 pi F RC here A, V into AF. That is V naught. Therefore, V naught by V in, that is A is equal to AF by 1 plus J 2 pi F RC, 2 pi F RC. But R and C elements are the filter network elements. Define another frequency term that is called as cutoff frequency. F is equal to 1 by 2 pi RC, 1 by 2 pi RC. 2 pi RC is equal to 1 by FH. 1 by FH. Therefore, A is equal to AF by 1 plus J F by FH. Where A is the V naught by gain of the filter circuit. First order low pass Butterworth filter. V naught by Vi is equal to AF by 1 plus J F by FH. Where V naught by Vi, gain of the filter as a function of frequency. Gain of the filter as a function of frequency. As a function of frequency. And AF is equal to 1 plus RF by R1, pass band gain of the filter. Pass band gain of the filter. Pass band gain of the filter. F is the frequency of the input signal. F is the frequency of the input signal. F is the frequency of the input signal. Fh is the high cutoff frequency of the filter. Higher cutoff frequency of the filter. 1 by 2 pi RC, that is equal to higher cutoff frequency of the filter. Like this is the next one, frequency response. We know that here one more important point here is A is equal to voltage gain or gain of the first order low pass Butterworth filter. We know that A is equal to AF by 1 plus J F by FH. Magnitude mod A, magnitude of that gain, mod AF by, that is equal to V naught by V in, mod square root of 1 plus F by FH whole square. At F equal to 0, at frequency F is equal to 0, mod A is equal to AF. Mod AF, that means AF. At F is equal to FH. Mod A is equal to mod AF by square root of 1 plus FH by FH whole square. That is equal to AF by square root of 1 plus 1 root 2. By using these equations, draw the gain frequency response of that first order Butterworth low pass filter. Mod A, magnitude of that gain at f equal to 0, that is AF by root 2. The gain is this one is pass band. This one is pass band. Take AF point, that means AF into 0.707. That this one is FH. This one is FH. This one is top band. Top band. The gain is a roll off at the rate of 20 dB per decade. Gain decreases. Gain decreases 20 dB per decade. Slope is minus 20 dB per decade. This one is F less than FH. F less than FH. Pass the gain is constant, that is equal to AF. At this one is F is equal to FH. The F greater than FH, the gain of that first order low pass Butterworth filter roll off or decreases at the rate of 20 dB per decade. The slope is minus 20 dB per decade. This is the analysis of first order low pass Butterworth filter.